rotation of the cylinder. So it's assumed that you're asked to assume that V is equal to the V phi is the phi corresponds to the cylindrical coordinate phi. Right? So all other components are taken to be 0. So the equation of continuity simply gives V phi is a function of RC and Z. Right? And I think you have further asked us to assume that neglect the dependence on Z. This will probably correspond to a very long cylinder. So the equation of motion takes the following form. So the cylinder is the inner cylinder, the axis, which is the outer cylinder. This has radius kappa times r. This has radius r, and you can take the origin between the bottom of the cylinder. So z direction is there. Right? So V is minus T E Z. So the new component of the body foot in the RC direction or in the phi direction. The phi direction equation of motion would be minus 1 over RC E by D phi plus mu times D by D RC 1 over RC and here you are asked also to neglect the dependence of P on phi. P is a function of R and Z only. So this would be 4 times Bz. Bz is simply minus G minus dP by dz. So I can immediately solve this and neglecting. There's no reason to actually neglect dP by d phi, but the argument given is that the question by virtue relation is that the centrifugal force drives the pressure gradient in the C direction. The gravity in the Z direction. There's nothing really to contribute to the pressure gradient in the phi direction. That's the argument we have given. So anyway, in solving this, I get dP by dz is equal to minus rho g, and I can then integrate this, and so I get e to minus rho dz plus that look at the dependence of P on phi. This is some function of Z. I'm sorry, function of RC. I don't know what notation has been suggested. Nevertheless, however, to integrate this, I need to find V phi, right? And so maybe just to simplify the solution, to decouple the solution of V phi from the pressure, and we need to make this assumption. So what I am getting is from the equation of motion, the phi direction. So this is very easy to integrate in ordinary differential equations and familiar equations. So it's very easy to integrate. So what I get is 1 over RC d by dRC. So RC is 5. Regular derivative is a constant, right? So let me call this C1. It is a constant. It is an ordinary differential equation. You can only integrate the constant. And so d by dRC is equal to C1 RC. Right? So now if I integrate this further, what I will get is RC defined is C1 RC squared by 2 plus C2. So if I divide 2 by RC, right, I get this. So here the domain is only between the cylinders, so I don't have to worry about a B5 going up at RC to the 0, because RC to the 0 is not a part of the domain. This is valid only for, we can't, we use the same argument we used in the earlier case, right? We go wrong. This here, that problem doesn't flow through a cylinder, so RC to 0 is very much a part of the domain, right? So here I can't cancel out that domain. I can't cancel out this term. C2 is not 0, it has to be found. But anyway, we've got now the solution, so I can sort of make this C1 prime. It's not a derivative, but so that I can make the C1 prime by 2 as C1, just to simplify, absorb the fact that 1 over 2 within the constant. So I've got now the solution to B5. Right? But I have to find the integration constant. Now the cylinder is being rotated, right? Both the cylinders are being rotated, right? So this is also the speed of rotation of the inner cylinder is omega I, that's what is given. The outer cylinder is omega naught. One of these can be 0, then you get a special case only one of the cylinders rotating. Right? So clearly, then the B5, the boundary condition, I need 2 boundary conditions. So those boundary conditions again will apply the no slip condition, but now the cylinder is in motion. Both the cylinders are in motion. So the would be equal to what? Omega I times KR, right? And then the phi of R would be omega naught times R. So that the fluid in contact with the solid will be moving with that velocity. That's the no slip boundary condition. Or the stick boundary condition. So the fluid sticks to the walls of the cylinder, so it's going to have the same velocity as that of the solid. It is now moving, not stationary. Right? So these are the boundary conditions. Now, apply these boundary conditions, I'm not going to do it. It's too constant. You can easily solve 2 linear equations and get the C1 and C2. The formula for the B5 is given in the book itself to be long-winded and here now I can get, so I have to really square this, right, and integrate this to get the pressure. First you will don't talk about this aspect, but it's very obvious that you can do it, but you get an integration constant which you just have to leave it as it is, right. So what I am trying to point out is f prime of RC, so F by drc is equal to rho times rho divided by rc and v phi square. For simplicity, I just write this as C1 rc plus C2 by rc square. Very easy to integrate, and I just have to expand this, right? So this would be rho by rc times C1 square rc square plus C2 square by rc square plus 2C1 C2, right? So we take the rc inside, I get rc and then rc cube and 2C1 C2 by rc. We are going to get C1 square, which we know, and C2 square, that this can be integrated. You get a logarithm also of rc, right? And then we get an integration constant. So that has to be substituted here. So the pressure can be easily found. I'm not going to do that. You can easily do the integration, right? We have somewhat long by the expression. The pressure is minus rho dz plus f of rc. So what I want you to do is to go and look into the version text where we solve the fluid rotating within a single cylinder, and there though you will get a very nice expression for the surface of the liquid. The top surface of the cylinder will turn out to be a parabola, right? I want you to look at that. That's a much easier problem to solve. Here you don't seem to get such a simple, revealing expression. Of course, it's valid between the two cylinders, the space between the two cylinders. That's the pressure variation. You've got dF by drc. So you integrate that, you get f of rc within a constant, and then substitute it, you get the pressure profile. You can easily plot it. At a given Z, you can plot how it is going to be with respect to rc between kappa r and r. I'll leave you to figure it out, right? So, but I want you to look at the analogous expression for the pressure, which gives a very nice expression for a single cylinder where the fluid is rotated within that cylinder. So that I will leave you to look at some words you later. Are there any questions? So there are two, or I would say three types of problems associated with any such situation. One is to get the velocity and pressure of light. So that's what we are focusing on now, right? We also saw, for instance, a simple case of flow down a circular tube. We can also calculate the flow rate. That's another calculation that you have to know in a given situation, how to calculate the flow rate. In situations such as these, there's also velocity pressure profile that basically comes from solving the continuity equation and the equation of motion together, the various approximations that we have seen. So it's not very easy to get analytical solutions unless we make these approximations. Then our calculation of the flow rate, then calculation of force, or in this case more appropriate is to calculate the torque that must be exerted on the cylinders, right, to carry out this motion. We will see how to do this later on. Because the simpler problem is one of calculating the force. The torque is just a bit more complicated. Right? So it's not, we need to go for the general expression, develop an expression in cylindrical or spherical or any coordinate, how to calculate these, and we'll make that look up later. Right? Now the equivalent problem, instead of two cylinders, if I have two spheres, that also is being asked to solve. So two concentric spheres which are rotated again with omega I and omega naught, right? And then if you see that if you write the equation of, let's now see what happens in that case. Right? So now we solve the equivalent problem of fluid between concentric spheres, and here you can solve, get analytical solution only in the special case of what are known as creeping flow. Right? So if you know what it means by creeping flow, it means that inertial terms are neglected. So here again we assume that V phi, V is equal to V phi. We are now working with the spherical polar coordinates, so you can just draw the inner sphere. Right? You can take the origin and we take this to be the z-axis. There is another sphere around it. The fluid is between the two spheres, the ocean between the two spheres. Right? So if you look at the continuity equation, all we get is d phi again by d phi is equal to 0, and so this would imply that d phi is a function of r and z, and here again we simply neglect the dependence on z. You should know what comes out of the continuity equation. What is an additional assumption we make? I'm sorry, it's not z, it's actually theta. Not doing any, we just have to retain as it is. It's not z, we just retain it as it is. And that's what we get out of the continuity equation. So let's see what further assumptions has to be made to get the solution that is given in first sequence. If we now look at the basic equation of motion, it can be written as a steady flow of a linearly viscous fluid. In any coordinate system, this is the equation. It is a vector equation. Now, for the spherical polar, I have to write these equations as 3 coordinates. So if you look at the r coordinate, this will give me rho times minus again d phi squared now by r. Is equal to minus dp by dr. Now I have to calculate the body force in the r and theta and phi direction. Now the body force, the z-axis is up, pointing upwards. D is again minus d times dz. The gravity force is acting downwards, right? So how do you calculate dr and b theta and b phi? Ez. What we need is actually the expression for Ez of E3, right? If you see, that's what we need actually. That if you see, if you look at the expression for the spherical polar coordinates, it's you can see these equations are now coming out to be handy even in solving these. In fact, it just gives you a comfortable way to get these components without having to worry about getting it geometry. You can do it geometry, resolving it in the theta phi direction. But this expression is very available. So what can you say about rho times b r? What would be b r? What is b r? That is b. So how do you calculate b r? How do you calculate the component of any vector in any line? Yeah, if you have to take a dot product, right? Br, nothing but b times er. That is the meaning of br. What I mean, the component in the r direction. Ez, what I mean is actually minus g Ez dotted with er. Right? Ez dotted with er is going to be cos theta. So I get minus g. You have to be careful about the sign. Now, if you look at the R equation, you will see that you won't get any other terms. No viscous terms will come. You can easily verify that. Right? So that is it. So then now I write in the theta direction. Now the inertial terms of theta direction is minus phi squared cot theta by r is equal to minus 1 over r dt by theta. Right? That's the gradient in the theta direction. And I'm just reading it out of the formula. You have a copy, you can probably get a copy of the formula given in the appendix of vertical length. When you come to the class at least next time, next week. Okay, so that you can easily verify how these are being written. I'm just reading it out from the formula already derived. Right? So, plus rho times d theta would simply be b dotted with e theta. So b theta is minus e z dotted with e theta. It is minus g times minus sin theta, which is g sin theta. This is a new thing that we have to know how to do it in a given. Today, of course, the cylindrical case CR and V theta will see when the person Z itself is one of the axes. When it's resolved in the other two orthogonal directions, it doesn't give any component. Here it's different. You have to be careful how to handle that. Right? So that is what it is, and it so happens again the viscous term turns out to be zero in the theta direction. You can verify that. Because in the curvilinear college, you have to be a bit careful in neglecting terms because there are some cross terms that come. But in this case, I think you can easily verify those terms to be zero because we have made this assumption. d5 is given by this. So now, so we cannot really neglect the dependence on beta as it will turn out. Now, when you come to the inertial term in the phi direction, it so happens that the inertial term is actually zero. And then we'll get minus 1 over r sin theta dt by d phi. And rho times d phi is actually zero here, as you can clearly see. Right? Because b dot e phi is zero. Ez actually doesn't depend on e phi, simply excluded of er and e theta. That's the advantage of having these analytical expressions. Right? You can directly infer these. Rho d phi is 0 plus, and then I have the viscous term. This would be the most important term. So again, I'm just reading it out from the formula already away. We didn't derive each and every one of these, but you can refer to the appendix in Wordsworth Lightfoot and get all these formulas. If you know how to read it correctly, right? So, which terms to neglect and which terms to come in. There be some practice. There have been occasions where I've given these formula sheets will be given to you in one form or the other in the exam. You should know how to apply it correctly, right? So this is what we have, and so this is the the point here is that in this case, what Wordsworth effectively consider is the creeping flow of a fluid, because the solution, of course, would become much more complicated if we have to retain these inertial terms. These are non-linear terms. You can argue how come we put that in the account there. Here we could get the solution. Right? So we consider the general case. Further, also there is a here the argument given was, right, the pressure gradient is driven by the centrifugal acceleration or centrifugal acceleration and the r direction and then the z direction by the gravity. Here if you see there is already the gravity effect driving in the equation. So we can probably assume that for low enough velocities, these can be neglected in comparison with the driving forces coming from the gravity. That's the approximation being made, right? So, neglect these energies. So, I've written the full equation so that you can see what is it that we are neglecting. Because the question is, why including it there, if we neglect it there also, we will not get even a gross behavior of the system. That's a critical term there. Here, because of the effects provided by the gravity, the argument made, these are neglected at sufficiently low velocity. This is what creeping flow means. Sufficiently low velocity. The inertial terms which are non-linear proportion to the square of the velocity can be neglected. That's the basic assumption. Right? So, and further, just as in the case of the cylindrical, you also here neglect the pressure gradient in the phi direction. We assume that dP by d phi is 0. Right? So then this equation becomes simplified, and in fact that's a way of decoupling again. Simplification that effectively decouples the pressure calculation from the velocity calculation. Now I have the velocity calculation here. The pressure can be very easily calculated. Here by integrating these, right? By integrating these equations, you can easily get the pressure, which is going to depend on theta as well as r. Right? So let's do that first. Pressure, what would you get out of the pressure profile? What is the pressure profile? Minus dP by dt r minus rho t cos theta is equal to 0. It means that dP by dr is equal to minus rho t cos theta, and T is minus rho t r cos theta, right? Plus some function of r, theta, right? Let's call that f of theta. Right? So now, to determine f of theta, I can now differentiate this. So we now differentiate this with respect to theta. This would be rho g r sin theta plus f prime of theta, and dP by d theta is nothing but rho g r sin theta. Right? From here, so first I'm integrating this, right? Getting an expression for p, calculating dP by d theta from that, equating it to dP by d theta from this equation, standard procedure. It's a clearly then f prime of theta is equal to 0, which means what does it say about f of theta? It's a constant, so I can simply say that I know the pressure within an arbitrary constant, which can be determined provided you give the pressure at some point. Right? So this is determined. Now what about the velocity? So the velocity you have to solve it using the cube to cancel out. So what you would get is 1 over r square d by dr, r square dp phi by dr is equal to minus 1 over r square d by d theta, 1 over sin theta. It can probably be solved by using the separation of variables method, which is again a linear equation. But it looks like a simple suggestion is given, whereby the standard assumption is seek a solution of the form of this form. That means, you can probably try, right, looking at d phi as a function of r times some, you've got it of that f plus some function of theta. see if you in fact get the f of theta to be sin theta. I don't know, it should probably work, but I haven't probably tried it. But what this says is takes that step and actually determines that function of theta to be proportional to sin theta. Right? You can verify. An indirect check on this. Directly, if you want to arrive at this, then you have to have some method of proving this. Right? But what is given here is, this is given as a sort of a hint for solution. Right? The trick is on the indirect check. If you use this, then you should get a differential equation in u of r. Right? So let's use that. So what we get here is I have d phi by dr is u prime of r sin theta. This is prime refers to derivative with respect to r. Right? And then I have r squared. And then, so r squared here can be cancelled on both sides. Right? So I have d by dr, which is now really going to be d by d. Let me make it d by dr. Right? R squared d phi by dr. So that will be r squared du by dr. Right? Sin theta can be taken out. Right? So we would expect the sin theta to come out as a factor on the other side also. Then the solution makes sense. Right? If we didn't know this, then we would have to determine this dependence in some other way. Right?
Can we make it equal to constant also? Because both each separately is a different function of one is function.
No. D phi, no, we cannot make this a constant because d phi is a function of r and theta. So both sides are functions of r and theta. That argument won't work. That we cannot do here. Right? So that's why I am reading the partial derivative here. D phi as such, there is nothing to suggest that if we probably assume, as often we have been doing neglect the dependence, that would be a bit careless because that would probably lead to an absurd result. Right? But here, d phi as of now, the very fact that we are suggesting a solution like this means that we are retaining both the dependence of r and theta on d phi. Right? Not making any simplifying approximation. So this is also a function of r and theta. This is also a function of r and theta. So we cannot make them both be equal to a constant, like we do. Right? But this is certainly probably, you can try this and see if you in fact get the f to be proportional to sin theta. That might work out. Right? So that is a more general way of approaching it. You're thinking, hoping that the separation of negatives will work here. So this is a linear equation. Right? And then the procedure in the separation of negatives to assume that this can be split into a product of two functions, one dependent on r and one dependent on theta. Then you might be able to infer the dependence on theta, that part has to be proportional to sin theta. But anyway, given this suggestion, let's see if it works out. So that would be minus, right, d by d theta of 1 over sin theta, d by d theta of d phi sin theta. Right? So d phi sin theta is actually u of r sin squared theta. Right? So d by d theta of d phi sin theta would be u of r 2 u of r sin theta cos theta. Right? 2 times u of r sin. So I am substituting this here. D phi sin theta will get sin squared theta. So the derivative of that is with respect to theta is 2 sin theta cos theta. So this gets cancelled. Right? And then I get equal to minus 2. U of r can be taken out because the partial derivative with respect to theta. D by d theta of cos theta is minus sin theta. So I get minus sin theta. And so minus and minus you can cancel. And so sin theta can be cancelled with the sin theta. So this shows that this is a correct guess. Right? The u, so I can now make this d by dr, right? So what we have is d by dr of r square du by dr, right, minus 2 u of r equal to 0. This is a differential equation, but it's not going to be a constant coefficient differential equation. So if we expand this further, right, we can do here. This would be, if I look this now, this would be r squared d squared u by dr squared, right, plus du by dr times 2r du by dr minus 2 times u of r equal to 0. Standard way to solve this, because you have this r squared d squared u by dr squared and then r du by dr is to the r power 0 u of r. Standard solution is to look u of r, a solution of the form r power n, a power series type, not power series actually, r power n. Because it's a second order equation, so you expect, you know, two linearly independent solutions must be there. So you get the quadratic for n is what you will get. If you assume this, right, so maybe c times r power n, let's say. Right, so du by dr is cn r power n minus 1 d squared u by dr squared cn times n minus 1 r power n minus 2. So now substitute this, right? So c is going to get cancelled out. So will r power n. You get common factor for all the terms. So you get n times n minus 1 plus 2, right? R will combine with r power n minus 1 again to give r power n, right? So that will be n
minus
2 is equal to 0. This will be n squared
plus n minus 2
plus
n minus 2
equal to 0. So that will be n plus 1 times n minus n plus 2 times equal to 0. Right? So these are the factors. So n1 is equal to 2 minus 2 rather, n2 equal to 1. So I can write the solution as u of r is equal to
C1
r plus c2 by r squared. So the solution itself is now obtained. d5 is equal to c1r plus c2 by r squared times sin theta. This is the solution. Now I obtain c1 and c2. And here there is a boundary condition. You have to be careful because for the cylinder, the surface of the cylinder, all points have the same radius. Whereas for the sphere, a point here, right, is at a different distance from the axis of rotation compared to a point here. So you will see that the boundary conditions here would be d5 and kr would actually be, we will prove this, omega I kr times sin theta, and d5 at r the omega naught r, or again sin theta will come. This corresponds to this. You have to remember this is r equal to now kappa r and r. But what determines, right, the velocity is depends on what point it is on the surface. Now it will depend. Not all points on the surface. They are all at constant r, but they are not all at constant rc. The rc in the cylindrical is what determines the boundary condition. You can clearly see that rc is nothing but r sin theta. That is why it is coming. So basically, what it is the same as in cylindrical. This is multiplied by rc, right? But here, right, this would be the rc for the inner cylinder. Any point would not only depend on in all of them are the same distance from the origin. The value of RC would be sin theta depending on what theta it is on the surface. Right? So that's the relation between the cylindrical and spherical coordinates that come in. That is what would determine the that would sort of nicely cancel with the sin theta. So maybe another indication to look for a solution of this form. Are there any questions? Okay, so this will complete the solution to the velocity and pressure difference for the sphere. Other problems we will discuss on Tuesday, but I would urge you to work through them because the hints are given, they are taken directly from words per Lightfoot. Especially assignment 5, the figures I have not provided. So you need to have a copy of words per Lightfoot at your side, chapter 3, right, of the second edition. You have that, there are guidelines given for the solution. I would urge you to work through that on your own. The answers are also given. Some in the assignment sheet 2 and some in the words per Lightfoot. So you need to verify those answers. So we discuss other problems in the next class. Yes, quick question. Huh? Yeah, no, that is just neglected. It is assuming that there is no variation in the finite. That's an assumption. I cannot really give a very rigorous justification for that. Just as we did for the cylinder. Right? So, I mean, the answer given, going by the arguments given in words per Lightfoot, is that there is nothing driving the pressure in the phi direction as opposed to the gravity, for instance, here in the R and P. There is also the viscous term there. Doesn't need to take that into account. Apart from the viscous term, you will have to argue that there is nothing driving, contributing to the pressure gradient. So it is neglected.
So,
yes.
Along the latitude of the sphere, P does not change. Rho P by rho pi is 0.
Yeah.
Along the latitude of the sphere.
Yeah. Okay, we have run out of time.